What variables at this monitoring site can explain the levels I've measured? What variables here can explain that level I measured there? If I find a consistent variable across all of these sites, that becomes my predictor variables. Therefore, if I move to this place that I have no measurement, and then I have all of the predictors there, I can quickly estimate exposure at that place, even though I have not actually measured. That is a summary of land use regression model. Okay? So basically, you have to do sophisticated statistical modeling, linking the measured exposure to some variables, either spatial or population level or temporal variable at each of these sites, and then come out with a predictive model. That model now is used to now estimate at all of our measured places. And something like this for the NO2 for ours will look like this. All of this stuff for something. These are the covariate. I'll talk more about the meteorological variables and some other things later on. So, if you're thinking of developing land use regression model, these are some of the steps you have to think about. You need to design your measurement, right? Limited money, so conduct measurement at some limited locations. Collect geocoded information, that is very key. You need to have a map. And all of your variables have to be able to be geocoded. In other words, located on the map. You can't do land use regression model without the map, which is going to be a challenge for many African countries. To get Gamma map from clean, organized Ghana map, or like from Greater Accra metropolitan area, from Ghana Statistical Service, it's a pain. And if Ghana is struggling with that, I know our fellow African countries, most of them don't have very good GIS maps. So that alone is going to be a limitation. It's a big problem. So you have to collect not just the measurements, you also have to think about all of the variables you are interested in, can they be spatially, or geocoded? Some of them are the temporal one, you don't need that, but the spatial one has to be. Something like traffic, how do you represent traffic? Maybe it is the volume, if you can count it there, if you have it. Maybe it's a road length, you're using an indicator variable now. Because you expect that in a high, major highway, the levels will be higher than maybe secondary highway. So you want to classify different type of information that may represent traffic, whether the road surface is paved or unpaved, okay? And then some population information, the density of people that are there, that will reflect the choice of emission factors that they are using. The land use type, is it commercial? What do they do there? Business district, and so on and so forth, and other variable. And then you need to link these two up, your variables to the measured information through GIS approach. Now, there are many ways people select the variables that go in. Some of them is just being practical. You wish you had it, we don't have it. Like Accra, I know they burn trash a lot. Even 2 days ago, behind the building here, they were burning trash, right? It happens all over, but we don't have information on it. I wish I had that, but I don't. So practically, I just have to let it go, right? So there are many approaches in selecting the variables. One of them will be you can do stepwise approach, machine learning and so forth and so on, but we'll talk a little bit about that later on. And then you have to assess how good this model is. And then after that, you now go and apply that final model to places where you have not measured and predict at those places. Okay? So in our case, this is what we have done. We were fortunate to have some good number of, how am I doing on time? Good, we'll be done soon. Some good number of spatial variable like greenness. Last time we were talking about here, greenness does not always mean reduction in PM, but in our exploration, we found that where you have more NDVI, which is an indicator of greenness in a space, is inversely related to the exposure. So more NDVI, less pollution. maybe it's actually socioeconomic status that is working its way through. Because in the high-income neighborhoods are the places you have the more green space compared to the low income. So you have to think about that even very carefully. And then we have the land use classification. We have the population density from the census, so we can estimate the number of people in a particular census tract or EA level. And we have other things like whether the bus stops, whether the malls, whether the restaurants, whether the churches. And then the road network, we need all of those. So you could see quickly, all of these have to be spatially aligned for you to be able to do your modeling part. So it becomes very important. So that is for the spatial predictors. Air pollution is also known to be, as we demonstrated in our exploration data, influenced by temporal factors, including something like temperature. Whether it's hot or cold can affect pollution. The wind speed and wind direction, relative humidity, rainfall, even the month of the year in our context is important. December versus is in June, they are different things. So you could have combination of spatial and temporal variables and be able to put all of those. So you start off with a whole universe of possible variables, and then you come out with an approach to select them, the best that will predict the levels at each of those sites. Operator? Just push it once, maybe. No? There we go. Thank you. Let me see if it's working out. Yes. So when we put all of those here in our group, this is all of the universe of variables that we're interested in at different level of estimation or understanding of them. We create a buffer, we estimate from all of those. And then the first thing is to see, are they really correlated with them? So this here shows you the relationship between these variables and how they correlate with the measured exposure. And you can see some of them have a high correlation, others don't have. So you can now feed this information into your selection process and let them select the strongest variables that actually relate to the measurements. So we did all of that. We used supervised approach, and then eventually we ran our regression model, and based on that, we test the performance of the model before we go to predict. So what we did in terms of testing the performance is this. We have at least 150 sites. We divide those into 10 groups. So let's say 50 each. No, 15 each, right? Our model, we take out 10%, the 15 out, and use the 90% to try to predict at those places, because now we have information real at those 10 sites. And I pretend I don't know what is happening there. I take it out of the model, and then I use the model to predict those places and see how good my model is performing, right? Does it make sense? I know what is there, but I remove it and pretend that it's not there and use my model to predict at that place. Because that's what I'm going to do at unmeasured places, so I need to test this first. And when we do that, you can see very strong correlation here between the predicted and then the measurement. Each time you take out the next 10%, you do the process again. You take out the next 10 until you complete all of the 100% of the data set. And then you do the summary. And it seems pretty reasonable compared to what people get in other places in the West. Based on that, our final model for NO2 becomes some information on road length within 100 meters near the measurement site, the length of a secondary road within 200 meters, NDVI, greenness, wind speed, relative humidity, the month of the calendar year, all of those are important. And based on that, we created now our surface. Okay, so we are done. Still not working? Good. Yeah, so now we have all of these pollutants, just showing you 4 of them, including even noise that we have created from the same approach. But remember, each pollutant will have its own set of variables that goes into the system. And then we have that. And now, there's a good thing about our model. It's space-time. So we have been able to predict at every 100 meters for every single week in that whole year. Now, if I can continue to extend that into the future, from 2019 going forward, I should be able to have estimate at every 100-meter grid in Accra for every single month across multiple years. And that is what we are doing. Then it comes back to what do we do with all of this, which I need to be wrapping up. The first thing we can do is to see, now we have the information, we can link it to some of the things that we're interested in. Does the pollution, is there any environmental justice issue happening? Clearly, our exposure vary by socioeconomic index across the city. Some places you can have as high as 10 microgram meter cube more, which is at the level of the WHO standard, between the poorest neighborhood and then the richest neighborhood. So that's an interesting thing to support what we know already in the world. And within Accra, if you look at the distribution of the population exposure, every one of them is above the WHO guidelines, which is what we actually saw from our own measurement as well. So we begin to see stuff going on there. Now, this is my final 2 slides. Now that we have this, we can do what Dr. Mustafa is asking us to do. We can now do some epidemiology, right? So we went to schools, we set up, we sampled about 1,000 school kids. We got information on their home addresses, GPS location, and then we got information on their school location, which is shown right here. So with this, because I already have a surface, once I know where you live, I can estimate long-term exposure at your school address or at your residential address. But we are missing the transit period though, but there are ways you can do that. And in fact, if the child tells me that I stay at home this particular week, this week I'm not in school, I'm home, I can actually do time-weighted average between the time they spend in different places and be able to estimate exposure for this person. And this is some example of what we got out of those school kits. And we have a bunch of information on them on blood pressure, BMI, spirometry, their lung health, and then also some neurodevelopmental outcome and sleep as well. So all of those data is now being analyzed to come up. And then the last thing we're doing is that, which I'm ending, we also setting up birth cohorts. There are not many birth cohorts in West African region. So we are ambitiously targeting close to 5,000 pregnant women, recruited from about 30 health facilities across the Gama. So these are the locations of the hospital. You can see what goes wrong if your GPS coordinate is not aligning with your information. So this hospital here is in the sea. Somebody messed up with a number. So you can predict that because this is outside. And these women here, we can't find exposure for them because they are outside of the Gama, right? So now we have all of this. This shows you the first 900 people from all of these facilities. So what can you do with that? A lot of information. You can study birth weight. You can study prenatal exposures. You can follow them into their developmental ages and have something about what happens when your mother was pregnant. This could link to some other outcome later in life. You can do all of those things. So Accra, for example, is ready to begin to explore all of this health information. And then also, if EPA is having plans for climate change, you can actually use this as a baseline. That in 2019, this is what we got. We have put in some intervention over the years. In 10 years' time, how do they compare? You can do some of those policy scenarios and all of that stuff. So it's a great way at the population level to be able to do this. That is your course in land use regression model. Thank you. Yes, I have 10 minutes for questions. So have I achieved my goal? You now know everything about statistics, you know about pollution, toxicology, and all of that.